Okay.
This meeting is being recorded.
Okay. Welcome to the GOAT seminar. Our today's speaker is Sanjukta, who will speak about fractional matchings and stability and optimality.
Yes. Thank you. Thanks, Sandra, for the introduction. Thank you for inviting me to give this talk here. And yeah, so I would just first give a disclaimer that the major part of my talk will be on this topic called fractional matching under preference and stability, and optimality. And at the end, I will also introduce some other problems and discuss some open problems in that area that I am open to work with. So yeah, so let's get started. So this is a joint work with Jiehua, Chen, and Manuel Sorge. We did it when I was in TU. And so the setup is as follows. You have a set of agents we want to be in, and you have an acceptability graph. So this means that agent in this example, agent B accepts agent A. So then there is an edge here from B to A, and this relationship is mutual. That's why it can be explained with this graph. And to denote the preferences of the agent, so that the setup we are in is akin to a stable roommate setup where you have agents and they have preferences over each other. So the preferences are not really an ordering of the other agents, but these are given by cardinal preferences, and which is denoted here by mu of x here. And what I mean by cardinal preferences is, for example, here B has a preference value of or satisfaction value of 3 over A and value of 1 over C. That means B prefers A more than C. And so the higher the value, the better it is, the more it is preferred. And the question that we ask in this setup is that to find a fractional matching which is stable. Now, what is a fractional matching? So you know what is an integral matching. Like the normal matching that we know is a subset of ages where the endpoints do not share the ages do not share endpoints, right? So we can write it as follows: that it's a match. It's a function m, the matching from E to 0, 1. That means 0 meaning the edge is in the matching, 1 meaning it's not in the matching. And this constraint basically tells you that look at all the edges that are incident on X, this vertex or this agent X, and that has to be at most 1. That means an agent cannot be part of 2 matchings. That is, a vertex cannot be part of 2 matchings. So as it is shown by this green highlight into this figure here. And now what would be a fractional matching? We relax this condition. So here it was this curly braces, we changed it to 1. So now our matching is a function from ages to some interval between 0 and 1, which basically means that you can take some age fractionally. So here this red dots here show that this, so this half dots, by this half dots, I mean that these ages are taken fractionally. So what could be the fractional values? So it could be the case that A is matched with value 1/3 with B and 2/3 with D. And this solid line here basically means that this is this age is matched with value 1. Okay, so this is what a fractional matching is. And now I'm saying that the task is to find a fractional matching which is stable. And stable, if you know that the stable basically means that you do not have a blocking pair. A blocking pair means a pair of agents who prefer each other over their current assignment or over the current matching. Okay, so I will explain in a minute what I mean by blocking pair in more detail if you haven't seen this concept before. So yeah, let's look at this example that we had in the previous slide. And the definition that I told you just now of blocking, according to that, do you think this green matching is stable? So it means that there is no pair of agents who prefer each other over this current matching.
AC is a blocking.
AC is a blocking because A is matched to someone with utility or satisfaction value 1. Same is C, but if they are matched to each other, they get a utility of 2 each. So SE is a blocking, so green matching is not stable. And for, you can believe me, for this particular example, there is no integral stable matching. Okay, so this is one of the motivation to look at fractional matchings, because in some scenario you want this to assign this yeah. So I'll also tell you one more motivation. Why are we looking at fractional matching? So think of this as a set of agents whom you want to put into some shifts together. So these are, like, for example, I'm showing here these agents as NARs, and they have to be put into some shifts but they have to be together. So they might not do their whole shift with one person, but they can time share. So this time sharing, any time sharing example where two agents has to be paired up with each other, can be modeled by fractional matching. So this could be like professor sharing his time slots of the day with students, and it could be this example with doctors or nurses. But we want to find an assignment, and there may not be an integral solution. So that's one of the motivation why we might want to look at a fractional matching instead. So the matching here I'm showing is a half integral matching. Why I'm calling it half integral is because the fractional values that I have assigned here are half. So, and you can check that this is a matching. No agent is matched with value more than 1. And but in this particular matching, every agent is matched with value exactly 1. Because if you look at this, so I'm drawing this figure above, just smaller here. So this is this A. So if you look at A, this is matched half here, and same for all these 4 agents on this cycle. So everyone is matched with value 1. Same for this G and H, they are also matched with value 1. So if this is the case, then we say that the agents are fully matched. So this would be analogous to a perfect matching that you would look for. So that means that you are not wasting anybody's time. You are matching everybody completely, fully. So now, okay. So now I had been using this word utility, but just to define it formally, that from a matching, agents get how much utility an agent gets is the sum of the values multiplied by the the matching fraction. So if I look at A here, so A is matched with fraction half with B, so it will get half, and A is matched with fraction half to B, so it will get 3/2. So half plus 3/2, it would be 2. And we can do this computation for each of the agents here. And so for example, for G, the computation is much easy, that you are matched with, G is matched with H, and the utility is 1. So 1 multiplied by 1 is 1. So for each of these agents here, we can do this computation, and that's what I have done, and written these values on the top of the agents. So this is what is showing the utility of the agents. And based on this utility, what we can define is called welfare, or it is also known as social welfare, is the total sum of the utilities that all the agents get. Now, if you are a designer of this algorithm, if you are and you want a happy society, you want everyone to be happy, you would probably want to maximize the social welfare. So this is so then your goal would be to not only look at so this would be one criteria that you might want to look at. So for this particular example, if you just sum up the utility of each of these agents, you get welfare related. Okay, just to get the idea more clearly, so this is another half integral matching, and I'm also writing the utility values here on top of the vertices or the agents. And so now so now I am saying that, okay, I want an allocation, there might not I want a matching, there might not be an integral matching, so I'm looking for the fractional matching. But why not one fractional matching enough? So I said in the previous slide that I'm looking for stability. So this example is to motivate that what are the criteria that we might want to look at. So one thing, as I said, is that I might want to look at a matching which has higher welfare, or which wants to match everybody fully. So, and as you can see, we'll see here for this blue matching, not every agent is matched fully. And can you see that? Which agent is not matched fully? Mhm. Who has the value 0? Yes, that's H. Isn't H? It's not matched at all. That's true. And then the welfare is also less than the red matching. So looking at any fractional matching is not enough if I want to have some criteria that it might satisfy, like maximizing the welfare or finding a perfect matching. So as I said that I will explain the stability concepts that can be studied here. So you might be familiar with the stable matching where the preferences are given like an ordering, linear ordering, but not the cardinal values that as I showed here. So in that setup, the stable matching, the stability notion is what I have written here. Sorry, the plus should be in between these two terms. It's in the front, I don't know why. So anyway, so this is the standard stability notion that is known in the literature, which basically says that the edge E is not blocking. So edge E is this edge XY, okay? And this edge E is not blocking. If I look, so when I said it in words, what I said is that XY prefer, it's blocking if they prefer each other over their current partners, right? So it will, what does it mean to say prefer each other over their current partners? So that means if I look at the agents, which are the blue agents here, marked by the blue edges here, they are they are the ones which are more preferred by X over E. So in this expression, this F are the agents which are more preferred by X over E. And if I look at the matching values there, the matching values assigned there. So if you think of it as an integral matching, there will be exactly one edge which has a value 1, or if it is a fractional matching, there could be multiple edges which has some fractional values summing up to something less than 1 or maybe equal to 1. So either this term has to be more than more than 1, or this term has to be more than 1. Now, if you look at these two terms, I'm basically summing up the XY edge twice, so that's why I have subtracted it. So it basically says that either X has to be matched with somebody better than Y, or Y has to be matched with somebody better than X. And now in the fractional setting, it could be that you are matched to multiple people, but with a higher, you are already fully matched, so you don't have any incentive, X don't have any incentive to get matched to Y. I hope this definition is clear. Do ask me if it is not. Okay, taking the silence as a yes, I'm moving forward. Next is the definition. So this is the standard definition that is already known in the literature and that is well studied. And so if we have this cardinal preferences, not only on the ordering, then we define two stability notions, as the title of the slide says, ordinally and cardinally stable. So I'll first define what we mean by ordinally stable, which will be more close to the definition of linear stability. So it says that if I look at the edges which are more preferred by X than this green edge, which is the E, then it has to sum up to 1, or the edges which are preferred more by Y, this orange edges, than this green edge, has to sum up to 1. Okay. So this basically, this in the previous definition, it was like you can have some fractional values here, and then finally that sum has to be less than M of E. But here it says that, okay, this particular green edge is not blocking if X is fully matched, completely satisfied, or Y is completely satisfied by the agents who are better than X, or X is completely satisfied by the agents who are better than Y. And the third definition, so I'm just telling you all the definitions in one go, and then we'll look at the different properties and why we are looking at these different definitions. So the third definition is cardinal stability, which has been introduced recently by Kargianis et al. And this says that, okay, so this is the definition that basically takes into account the utility values. So far, the definitions that we looked at, the stability notions that we looked at, they were still talking about the preference as if the preferences are ordering. But because here we are only looking at this ordering, we are not looking at what are the values of this. So it could be the case that F is an edge which is very slightly preferred more than E, but it would still be counted here. But this is the definition which is more appropriate when you have cardinal preferences. And this definition says that I look at the utility. This is, if you look at this basically is the definition of utility that we saw in the previous slide. But yeah, so if I look at the utility of X, so this basically means that X is in this edge F. And if I look at the utility that F gets from these edges, it should be more than what it would get if it completely gets matched to Y. Or the utility that Y gets from this matching should be at least how much it would get if it gets completely matched with X. So basically, it means that if they want to get matched to each other, that is, if they want to get matched into this edge E, they would not improve. Their utility value will not increase. It would at most remain the same, at least for one of them. It might be the case that for one guy it is improving, but for at least for one of them it doesn't improve. So they do not prefer to get matched with each other, leaving the current assignment. So this is the whole notion of stability. That why we want stability is that as a mechanism designer, I am giving some assignment, and I do not want that people to locally change their assignment and not create a chaos. So this is why I said that in the context of when you have cardinal preferences, this is a definition which is more suitable to identify the stability. So okay. So now we get back to this example, and we saw that there is no integral matching here, and this is a half integral matching, and so this particular red matching is cardinal stable, and you can check the definitions with this, or just in the interest of time, you can trust me. So this is, and as we have seen that these are fully matched, all the agents, but is this matching ordinally stable? I already brought it up. So this matching is not ordinally stable because the edge DG, which is this edge, right, is ordinally it's blocking. And can you say which agent is improving or what is happening here? G is definitely improving, yes, because if G gets matched to D, G will get 2. But if it is blocking, both has to improve. So what is the right? Why is D improving?
You'll just give up the edge with A.
Mm-hmm. Yes. Right. So if it just gives up the edge with A, as Andre said, then also it will improve. But we want to say that DG is blocking, so it's basically giving up both this half, and it's getting fully matched with G. But it will still improve because, yeah, previously it was half plus. Oh, we are looking at ordinal stable. Sorry. So previously, yeah, it was. If I am looking at the edge DG, then it is not fully matched, just with C and G, because with C it is matched with half. So it will be ordinally, it will still prefer to get matched to G, as this definition says here, right? And so now the question could be that does there exist a matching which is ordinally stable? So the blue matching I showed before is both ordinally stable and cardinally stable. So, okay, so we have now seen 2 examples where one is cardinally stable but not ordinally stable. Another example where it's both ordinally and cardinally stable. So what does it mean that ordinal stability always imply cardinal stability? And this is why, so let's look at the properties. So this is indeed the case that ordinal stability always imply cardinal stability. So if it is ordinally stable, then it will be cardinally stable, because as you can see that here, we are basically ignored the utility values, and we wanted that it get matched to better, more preferred agents. and it gets fully matched to more preferred agents. So if it is fully matched to more preferred agents, it's just calculations that if it is already 1 here, if you multiply these values, then it would obviously be more than this, because these are fractional values which sums up to 1. Because it is ordinally. If it is ordinally stable, the fractional values here will sum up to 1. So this will, if this utility, if they are better than this green edge, then this will definitely be more than this. If it is confusing, I can just write it down. So why is this? Why is the case that this implies this? So what does this say? That if I'm looking at this edge xy, right, and I am looking at all these agents. So this is my green edge E, and these are all the agents who are preferred. So this is F, which are preferred more than E. Now, if this, so ordinal stability says that this must sum up to 1. So sum over F, X is in F, and F is preferred more by X than E, M of F, this sums up to 1, right? And what does cardinal stability says that I'm for cardinal stability, I have to look at mu of how was the notation? Mu underscore X and F M of F, since that F is more preferred by X than E, and this has to be more than mu X of E, right? So now if I just multiply it both sides with mu X of E in this equation, so from here I'm multiplying both sides with mu X of E, F, and this is equal to mu X of E, and now this quantity is greater than, so since mu X is less, so this, because I know F is preferred more than E, so mu X is, so since mu X is less than equal mu X of E is less than equal mu X of F, I know that this quantity has to be less than sum over mu X of F. I know that. Right? And this is what we need for to show that this is cardinally stable. So yeah, it's just a easy exercise to see that if it is ordinally stable, then it will be cardinally stable as well. And for integral matching, if they are stable with the, which I introduced as linear stability, the classical notion of stability, that also implies ordinal stability and cardinal stability both. This can also be seen easily. And yes, so another result that this is something which you prove is that ordinal stability and half integral matching always exist. And if you are familiar with the stable matching literature, you might guess how this result can be proved, but I will also show you, we'll go into that. So yes, so as I also indicated that we might not only want stability, but we might want to have some optimization criterion, like maximizing the welfare, or maximize, do not want to waste resources. So I want to get a perfect matching, and something close to perfect matching in this setup would be called fully matched agents. So maximizing the fully matched agents, which is also, you can think of it as maximizing the size of the matching. So these are, yeah, these are just formally written, the statements of the questions, that basically the first question says that you want to maximize the welfare of the, as you have seen, the welfare is basically the sum of the utilities of the agents. And the second question says that your matching has to have at least how many fully matched agents. Okay. So the first question was already introduced by Karagiannis et al. In their paper, and the second question is this perfect matching question is something which we start to study. And we can, okay, so in this question I'm writing it here for ordinally stable roommate. So okay, I would just say that a roommate means that the example that I'm saying that agents have preferences over every other agent. This is what is called the roommate setting. And marriage setting would be that you have two sets, A and B, and A have preferences only over B. So your acceptability graph looks like a bipartite graph. So if that is the case, then this is called marriage setting. And this is computationally, it has been shown that it has been seen that some of the questions are easy for marriage setting, whereas they are hard for the roommate setting, where this graph is not bipartite graph, but a general graph. So, and all these questions, both of these optimization questions can be asked for the roommate setting, that is for the general graph, or for a restricted version, which is the bipartite graph, which we call the marriage setting. And okay, so some of the related work. I don't know, how much time do I have? Okay, that's good. Okay, I'll just go quickly over the related works then. So the structural properties of linear stability and their so linear stability is what is known classically. So this has been, as you can see, has been studied for a long time in the literature. And ordinal stability, although not exactly into this form, has already been introduced in so it has already been introduced in 2006, and some of the properties has been studied as well. And the existence of ordinal stability when the satisfaction values are not same for two agents. So this ties basically means that you have an agent, say U here, and you have agent V1, V2, and for U is connected to both V1 and V2, and U gives same value. So U gives value, suppose 2 to V1 and 2 to V2 both. So if this happens, then we say that there is tie. And if all these values are distinct, then we say that there is no tie. So it is known in the literature that when there exist ties, some computational questions becomes hard, and which are generally easy in absence of ties. For example, if it is a bipartite graph, finding a stable matching is linear time solvable when you do not have ties, and finding the maximum size stable matching is also linear time solvable because size of all the stable matchings are the same. But if there are ties, then size of all the stable matching are not the same, and finding the maximum size matching would be NP hard. So this is why what I mean when I say that there are some computational problems which are hard when you have ties. So this has been shown that the finding an existence of ordinal stable matching without ties in hypergraphs, maybe you can just ignore this now for now, as it always exists, but it is PPAD complete for finding one. And so these are the results that we show. So these are the existential questions which has, so the green ones are which we show, and the others are which had already been known. So as I said that for the no ties case, for the ordinarily stable marriage case, it has already known that it always exists. We show that when you have ties, this always exists as well. And for the cardinal stability, also for the marriage case, it was shown by Karagiannis et al. That it always exists. We show that the roommate setting, it always exists as well. And for the optimization questions, we look at this maximizing the fully matched agents, and this question is just most of the optimization questions are NP hard, and these are the ones that has been shown by Karagiannis, and the others are shown by us. And yes, so for the marriage case, I would just like to point out here, a fractional matching can be seen as a linear composition, or what is this? How is it called? yeah, it basically it can be decomposed into integral stable matching. So it can be
Convex combination.
convex, yeah, linear combination, not only just convex, linear combination of integral stable matchings. So that is the result which we show, and that is why we can get this polynomial time results for the marriage case, but that is not true when we are in the roommate setting. So this is also, if you if you are familiar with the literature, there is something called mixed matchings, and this is why this is different, because a mixed matching is something which can be written as a linear combination of integral matchings, but you cannot write every fractional matching as a linear combination of integral matchings. So I mean, you can only do that if it is a bipartite, the marriage case. For the roommate setting, you cannot do that always. Yeah, so right. So, and in the structural properties, we also show that for the without ties case, this ordinal stable marriage has this lattice structure, which exists for the classical stability concept, and the roommate also have something called a median property, which again exists for the classical stability concept. And yeah, this is just an observation from the table that ordinally stable matching computational seems easier than cardinal stability, and our hardness result hold even for the marriage case. Yes, so this is something that this is why I also mentioned that in general it is shown in the literature that or it has been seen in the literature that the without ties case generally becomes easy, but if we look at this particular column, both these problems are computationally hard, I mean NP complete. And this is a bit surprising, because if you think of maximizing the size when you do not have ties, which would be analogous to this question, this is polynomial time solvable for classical stability. And even maximizing welfare, egalitarian, everything is polynomial time solvable for without ties for classical stability concepts. So yes, this I would say is a surprising result, or it kind of shows that the hardness doesn't come from the ties, but it comes from the fact that the utility values are cardinal values. Okay, so yeah, we also show some approximate result, and I will go into the detail of this particular result, but I will just give a very brief overview. So for this result, we need to know this notion of stable partition. I'm assuming people are not familiar with this, but I wouldn't say much in a lot in the interest of time. What I just want to say is that it is basically a permutation which satisfies some properties. And and if you know permutations, you don't have to know what is stable partition. You know permutations, and you know permutations can be seen as cycles, right? Who is matched to who is like yeah. So suppose you have this number 1, 2, 3, 4, 5, and you write a permutation of this 5, 2, 1, 3, 4, and then you can write the permutation cycle here, right? So now this particular for this stable partition also, you can think of it as cycles and singleton vertices or disjoint edges. And if you have that, then it was shown by Tan that if you have this, and then in polynomial time you can find this cycles and disjoint edges and singleton values. So what you have is that you have some cycles, you have some edges, and some singleton vertices. And if I match these edges with each other, so if I match these edges with each other, and if I match this cycle half integrally and leave these singletons as isolated vertices, unmatched vertices, then this is a stable matching. But if you are looking for an integral matching, I said half integral. Okay. So this will give you a half integral matching, right? But if this is, suppose the cycle is a 4 cycle, then it can be shown very easily that you can easily decide which 2 edges to pick to integrally match them and make it an integral stable matching. But if it is a size, suppose it is a triangle, then there is no way that you can integrally match them. So the only way is to match them half. or with some fractional values. Oh no, just half. Yes. So this is why there always exists a half integral matching, which can be obtained from this particular partition, which is called the stable partition. And what you basically do is this, as I explained here, that if you have a odd cycle, you basically assign half to each of the edges. If you have disjoint edges, then you just match with each other, and the singletons you leave them isolated. And for even cycles, you can easily find out which edges to match to each other. So, and this could be done again in linear time, linear in the number of edges. So if we, and what we show is that the matching you get by doing this, the process that I explained, this matching is ordinally stable, and as a result, it can be solved in polynomial time, and also it matches the maximum number of fully matched agents. Like it also maximizes the number of fully matched agents. So okay, should I give the proof or not? Okay, I can try to give a little bit of idea of how this proof works. So yes, so what we do in the first step is this, that you have this acceptability graph. Suppose this is your acceptability graph, and you have some agents. So I am looking at this particular agent Y, and it prefers X the most, and then there are some other agents. And then I'm looking at this, I'm looking at preference list of X, and X has Y here somewhere, and then there is W. So if, suppose X is matched with W, since Y prefers X the most, it would always try to get matched with Y, and Y is not matched with X, rather X is matched with someone worse than Y. So this will always be a potential blocking. Or rather, in the classical sense, this will always be a blocking. So in the classical stability, we can always assume that I can delete this XW edge, or rather I can remove W from X's preference and X from W's preference. So this is the first step that we do, that if there is such an agent X and Y, such that X is Y's first preference, and there is agent W, which is less preferred than Y in X's preference, then we delete W. And this is also the first step that is performed by the stable roommate algorithm of Arvin. So, and so this is after we do this. So, and this is necessary because this this is necessary for the correctness of this step. So after we do this, we will try to find a stable partition. And so after we did this, these are the blue vertices are the isolated vertices, which we have deleted. So it could be W because we have deleted the edges on it. And then you have this red vertices. And now, yes. So as I said that So in the classical stability, it is clear that none of these W agents that I deleted from the preference will be matched. And so now this is my partition, suppose, this green lines. So I have this cycle, the green dotted cycle, and I have this disjoint edges. And as I just explained, that I will assign half values to this dotted cycle and do this to this, like match this one with value 1, 1, 1. And okay, I do not write anything else here. So to see why this is ordinally stable, so okay, I'll probably not go into the details of why this is ordinally stable, but I can tell you why this is fully matched, right? So and this is basically by this observation that none of these blue agents that I have deleted, like that have become isolated after my first preprocessing rule, can be matched in an ordinary stable matching. So, and every agent that is not isolated after this first preprocessing step are matched, and they are matched fully, because either they are in a edge. So they are basically integrally matched, or if they are in a cycle, since I'm taking half on both of its edges, both of its neighbors, then it will be fully matched. So this basically, so this observation basically tells that since I cannot match any of the blue agents and the remaining agents I have matched fully, so this basically maximizes the number of fully matched agents in a ordinally stable matching. And as I said, that this can be found in linear time. So yeah, so now this, yeah, so I will go into some of the open questions. So this is the summary of what we saw, and so as we saw that all these questions were NP hard, even without ties, and we also look at some approximation hardness, but the parameterized complexity of all these problems are open. For example, say parameterized by the welfare value, or parameterized by the total number of if we are maximizing the fully matched agents, parameterized by the number of agents. But yes, so these are open. Also, we didn't look at any preference restriction for this particular model. So in fact, not only us, like the preference restriction, structured preference has not been looked at for cardinal models at all for stability. And this is also a wide open domain to look at, because as we saw that the problems are hard, so there could be that for structured preferences the problems are tractable, that is solvable in polynomial time. Okay, so now how am I doing with time?
10 minutes.
10 minutes. Okay, so now so these are the problems that we can look at into this particular problem, and there are some other open questions that I also want to say. So if you still have some interest in looking at open questions, so then I'll just switch the topics, because there are many other topics which I'm currently interested in and I have recently worked on, and so these are some related to something called stable committee. And a stable committee, as we saw that, okay, so we just saw stable matching. So a stable committee can be defined in many ways. So as we saw, here's different descriptions of stability for a matching. A stable committee can be thought of so if I have a set of agents, which are the candidates, and I pick this subset into the committee, then there is nobody outside the committee who is preferred by majority of voters than somebody in the committee. Did I make myself confusing? So what I'm saying is that I have a set of candidates. So suppose the election of, I don't know, department president or something is happening, and this is not that this doesn't happen in one step. You first select a committee of faculties, and then that committee of faculty selects the presidents or something like this. And then everybody votes. And I say that a committee is stable if there is not a member who is outside the committee, but a majority of voters prefers this member compared to some member who is in the committee. So then the voters will say that, okay, bring this guy into the committee and leave this one out, right? So this could be one notion of stability. There are many other notions of stability. One is particularly motivated by proportionality, that if there is, so you could think of it as an election, like the political elections, and which are electing the president of the country or something. And then there is a fraction of people who are the minority, or they do not get any representative into the house or into the legislative. So to avoid this, you would want to have a committee who is proportionally representing the voters. So if there is a 1/3 of, or say 1/4 of voters are voted for somebody, and there would be some representative for this set of voters. So this is something I'm saying it very vaguely, because I just wanted to be quick, but so there would be a notion of proportional representation. So that could also give you some notion of stability. And now this different kind of stability has been considered, but one thing, as far as I know, there has been only one paper or maybe 2-3 papers in the last recent years which is studying fractional stability, which means that a person might not be completely elected. That is, he might might spend half of his time as the committee member, and another person spend half of his time as a committee member. Yeah, so this could be so this has been studied, so there has to be some motivation for this as well. But yeah, so this could be one set of open questions, because how do you define fractional, like the stability for the fractional setting, what makes sense? And then there could be different notions here. Okay, so another question again with respect to committee. Okay, committee is also called multi-winner election. Sorry, I should have stuck with the same wordings. But yeah, so the bribery problem for multi-winner election, I think it has been studied, but in a very limited fashion. So what I mean by bribery is that you have this particular preferred agent P, and you want to create a committee such that P is in the committee. And now you want to bribe some voters to change their votes, or yeah, you can. So and then can you make P into a stable committee? I see Dushan is saying a lot of things, but I don't know what.
It's kind of limited. You can also want some preferred candidate not to be elected.
Sure.
Yes, you can also do that. And then, okay, so then instead of just one preferred candidate, you might have L preferred candidate, and you want at least K prime of them to be in the committee. And this could have some motivation, like you always want your agenda to pass through the committee. And if you just put one of your guy, that's not good enough. So you at least want K prime of them to be in the committee. Another thing could be that you have an ordering of this preferred candidates, and you want to maximize the Boda score. How do I say Boda score? So you have this preferred candidate P1, P2, PL. And if this is the ordering of your preferred candidate, the Boda score for this guy is 0, the next guy is 1, and so on, and this guy is N minus 1. So now you want to choose a subset of preferred candidates of size at most K prime, such that the sum of these values are maximized. So yes, or at least B or something. So this could be some questions related to committee. And yes, there are some more open questions, but if you're already saturated, I would pardon everybody to not listen to me anymore. But if you want to know, I can still go on. So okay.
Thank you.
Thank you.
Any questions, comments?
Like any technical questions related to anything that I explained that you didn't understand, or any question related to open questions or anything? Yeah.
I would like just to note that the bribery was introduced by Edith Albert, and the scholarship scheme was by the Eastern people.
But is that was bribery, like the bribery not in multi-winner but in single winner election, right? Yes, I think that's
Somehow
He was doing his PhD with Thomas Pandras.
yes. And I think control and bribery all are introduced by this set of people. Yes, that is true. Okay.
Yeah, if there are no questions, then let's think again.
Thank you so much for your attention.